Shut up.
What? I don't know. That was pretty
Lab 2, charge tapes revisited. This experiment builds upon what we learned from the first lab, where we observed how charge tapes interact. We will take a deeper look into modeling the behavior of charge tapes. Purpose background. The purpose of this lab is to expand upon the findings of the first charge tapes experiment by using a computational model in CoolScript. This model divides the tape into small segments and treats each of these segments as point charges. By doing so, we can more accurately model the distribution of charges along the tape. In terms of the process we use, Newton's second law gives us the relationship between force and acceleration. Newton's third law reminds us that every action has an equal and opposite reaction. We also use the electric field of a point charge equation, as well as the equation for electric force. Finally, the superposition principle allows us to sum the electric fields from each segment of the tape to get the total effect. Here are the main results from the experiment. In Lab 1, the charge Q on the tape was approximately 8.7591 times 10 to the negative 9 coulombs. With the updated model, we found that the charge Q was 240.156% of this value, or approximately 2.10124 times 10 to the negative 8 coulombs. Also, we found that the gravitational force acting on the tape is equal to the electric force, which is a key result from the experiment. In terms of assumptions, we ignore air resistance and assume that each U-tape has the same charge. The charge is evenly distributed across the length of the tape, and we treat the tape as if it's divided into equal charge segments. Here are some physical parameters we use for our experiment. The tape's width is approximately 0.017 meters, and its length is 0.17 meters. The mass of a tape was measured to be 0.0000175 kilograms, and the distance between the tapes was 0.022 meters. The image on the right shows the results of the electric and gravitational forces acting on the tapes in the model. Moving on to the code used for simulation, we use GlowScript to simulate the charge taping system. Here are some key sections of the code. We define physical constants such as Coulomb's constant and gravitational acceleration. We also input the observed values such as mass, width, length, and distance of the tapes. In this section, we define the function to compute the electric field and force from the charged particles on the tape. We use the line of charges model, where each small segment of the tape is treated as a point charge. The function calculates the electric field at each segment and then computes the resultant forces. This is the rest of the code. For the results, we see the output of the computational model, where the electric force and gravitational force acting on the tapes are equal. The electric force was found to be approximately 1.7264 times 10 to the negative 3 newtons, and the gravitational force was 1.7656 times 10 to the negative 3 newtons. This confirms our hypothesis that the electric force matches the gravitational force in the setup. What if? Now let's consider what if we had modeled the tapes as a single point charge instead of a line of charges. In the point charge model, we previously found the charge to be 8.7591 times 10 to the negative 9 coulombs. However, using the line of charges model, we get a more accurate value of 2.10124 times 10 to the negative 8 coulombs. And why? Why do these estimates differ? Which value is more likely to be closer to the real value and why? The estimates differ because they use different values of precision. The line charge model is more likely to be closer to the real value because it uses smaller step sizes and is more representative of the actual charge distribution across the tapes. This better represents real-life conditions. In conclusion, the line charge model provides a more accurate representation of the charge distribution on the tape, leading to more precise results for the electric force. By comparing these models, we gain a deeper understanding of how charged objects interact in real-world scenarios. Thank you.